请启充话筒。
Welcome to the physics talk. So you'll recall it, what we talked last time. So last time we talked about the physical states. Physical state can be represented by the cat, so in a bracket notation. And we also talked about the observables. Observables that is represented by the permission operators. And one thing we didn't talk about it is there is the active field of research trying to find that an observable is not an observable that is not representing by the Hermitian operator. So there are some cases, indeed the observables is not represented by the Hermitian operator. We didn't talk about it, but in our case, we will assume that all the observables is represented by the Hermitian operator. And also talk about the basis, and now we will wish to move on to the matrix representation and also the measurements you want that I wish to cover in this today. So to start with operator. An operator, in general operator, there's no need to be a Hermitian operator. In general, the operator we write as X, and we impose the identity operator in the both sides of the operator. So in the sense that we have the base cat, we have the base cat of these two, and it sum up with index I and J. If we, let's say, the dimension of the cat we want to represent the physical state is that in a dimension n, so we'll see that the matrix representation of that operator is have total n square entries. It's a square matrix. So in the sense that when we write down in this form, the X operator, the component of the matrix can be written as when we're running the index I and J from 1 to n. So in the sense that this one we treated, the front part is a row, row 1. Let's say the row 1 and column 1 comes the list of the entries, and we let it arrange in that matrix representation. So that the X operator will become a square matrix. And here we choose the set of the eigencats as our best case. So the form of the matrix representation of operator X will depend on the choice that we use in the base case. The next one we will see about it when we multiply two operators together. Suppose we have an operator Z can be expressed as the multiplication of the two operator X, Y. And this will give us that the Z is one. Yeah, we insert the identity operator in between the X, Y. So yeah, and this can be seen as we getting the matrix of Z getting the matrix of Z when multiplying the matrix representation of X and Y, X times Y, and getting the matrix Z. So in the sense that when we present this as A1 X, A1, etc., and same goes for the operator Y. The multiplication of the operator XY in matrix representation is just the multiplication of the two matrices, give us the matrix representation of operator Z. And now we move on to the CAN. Suppose we have the operator, suppose we have operator X that's acting on a CAN, which will give us another CAN. So we want to ask how it can be represented in matrix form. So let's say we want to use the basis in this. So to attempt the matrix representation, to obtain the expansion coefficient of the cat gamma, we sort of multiply the bra on the cat gamma cat. So and this will give us when we multiply the bra here on the left side and also the right side. And we insert the identity operator in between the here. And when we seeing this in this form, we can treat as this is the entries of the matrix representation of operator X, and this because this index can be running from from 1 to n, let's say it's n dimension. So this can be seen as another matrix, which is a row 1, will have a row 1, row 2, row 3, row 4. So it will be presented as the column matrix. And same goes for the gamma cat. And gamma cat, because the index I can be running from 1 to n, we can represent it as a column matrix also. While for the matrix, how about the matrix representation of the bra? So suppose we have another we have operator is acting on the bra, give us another bra gamma. So same goes for then we let's say we want to represent it in the basis of this bra. And we sort of multiply it again in the right hand side, on the right hand side of the equation 1.7. So and inserting the identity operator in between. And again, by seeing that these two have an index of I and j is running from 1 to n. So this can be this is row, this one is column. So the column is 1, 2, 3, 4, and we represent it as row matrices. So, but then when we talking about the when we represent it in the row matrices, usually we will write it in another way, the sense that we use the properties, skew symmetry properties, the inner product interchange gamma, let's say gamma A1. A1 is interchange become A1 gamma. Yeah, we have this property of the inner product. So to interchange all the entries to represent the bra, to represent the bra in the matrix form. While for the inner product, For the inner product, we insert identity operator again in between the beta and alpha, and this one will be the column matrix. So this one is the row matrix, right? And this one will be the column matrix. We're running the index I here, and we interchange the inner product again in using the skew symmetry, so we can see the inner product of the alpha and beta between alpha and beta is the multiplication of row matrices and column matrices. And just want to verify that the inner product, when we represent it in the matrix form, in the sense that when we multiply it all the way along, and we taking we want to verify the skew symmetry of the inner product at the end of the verification. So it's just we sort of pulling out the star, pulling out the conjugate here. So this one we pulling out, and this one conjugate is we cancel out. And because this two is the number. This two is a number, so we can interchange between two of it. And again, we seeing it as the this one is multiplied to a matrix. The component multiplied with the component, and we can write it as the row matrix multiplied to the column matrix. And again, this one will be we conform the skew symmetry of the inner product. While for the outer product, when we have outer product of a cat and a bra, again we start with insert two identity operators in between, not in between, at the end of beta and also alpha, the summing of an index of I and j. Again, we interchange this with a skew symmetry. And if you're looking at the this one, this will be our components. So these will be our entries that we want to put in our matrix representation. Yeah, so the matrix representation of the outer product can be written as the square matrices. So suppose we have a Hermitian operator. Just now we are talking about the general sense of the operator. Now we will limit to the Hermitian operator. Let's say we have A, and A has a eigencats, which can be we want to use it as a basis. When we use when this Hermitian operator using this eigencats as a basis, again we want to try what is the form of the matrix of the Hermitian operator in this basis. So by inserting the identity operator in the operator, by inserting the identity operators at the end, at the both end. So this will be our this will be our entries of the matrix representation we want to put in. But if we because we are assuming that we are using the basis we are using is eigencats, in the sense that when we adding the operator A, on a cat, it will give us the eigenvalues which we can
is a number which can pull out. And these two will be the inner product between the two cats, which is autonomous to each other. It is autonomous to each other. And if we're saying that when if we're taking the index, we will see that this the autonomous, sorry, let me repeat again, the autonomous probabilities that give us when the index running I equal to j will give us two values of 1. When I not equal to j, the the terms will be vanished. And obviously you can see that when the omission operator when it represented as the matrix using its eigencats as a basis, it will give us a diagonal matrix. Next, we should talk about some measurement. The measurement, we assume that let's say we have an observables A. We want to measure what is, let's say that observable A can be the momentum, can be the position that we want to measure on system. Let's say it's a particle. The physical state is represented as the cat, which is encoded the information that we want to measure, as we talking about in the last 2 weeks. So this physical state will be represented as a linear combination of the eigenstate of the A. So sometimes we are calling it as the superposition of eigenstate of A. So when we are doing the measurement of A in the physical world, the physical state will be thrown into certain eigenstate. So in the sense that this will result us as give us a result of a measurement as the eigenvalue. The eigenvalue is our result of the measurements of observable A. So so let's say we have a different it's important to point out that before the measurement we don't know which one will be because we have different state. There is different possibilities. The physical state can be thrown to the any of the eigencats. So when we want to know that what is the measurement, what is the result of measurement, we need to do the measurement. When we do the measurement, this act of measurement will affect the original physical state, which is at the end will be thrown into the one of the eigencats. And so we're talking about many of the properties that in the past few weeks, we do postulate that the probability of the state to jump into one of the eigencats is expressed in this. The probability of let's say jump into the one of the eigenstate of AI is the inner product between the physical state with the eigenstate AI, and we're taking the norm square. In the sense that we want to normalize it, we want to normalize the physical state because at the end, if it is not normalized, as we will see later, this the total probability of getting each one of the eigenstate will not equal to 1 if it is not normalized. So although we are talking about one single physical state, if we want to determine the probability of certain physical state to thrown into one of the eigen state, we need to do the great number of the measurements on a same physical state. Let's say it's not possible that let's say we do the measurement A and we do the another measurement again. This one will give us the same result, and it is not the same as we are talking about we doing the measurement on um, same physical state before same physical state before it changed. So maybe they see one of the some of the examples. So suppose that we have a cat is AI. The physical state is AI itself before a measurement is made. So let's say we want to measure the probability of getting AI when on a physical system, which is initially as is in the eigencat of AI already, is in that state already. So by intuition, we will think that the state is already confirmed that it's in AI state. So the probability of getting that AI state is must be equal to 1. So by mathematics, when we taking the physical state here is equal to state of AI already. So when taking the inner product, it gives us equal to 1. So it match with our intuition. So in other words, when we do the repeated measurement on the same observer, the physical state, let's say we have a physical state alpha, we do the measurement A, let's say we will get the AI already. So if do another measurement A again, is inside this case, we're taking the inner product between the physical state after measurement with the they want to measure. So the successive repeated measurement on the same state will give us the same result. So suppose that now we have a same physical state, which is in the state of one of the eigencat. Now we wish to know that what is the probability to measure the state, the physical state, which is in another eigencat. Let's say is eigenstate. Let's say is AJ, where J is not equal to I. So it's like we have a physical state which is in AI already. We want to do the measurement A. So we want to measure the probability of getting the AJ. So the probability because of the orthogonality of between two states that we are assumed before. So when we're taking the inner product between these two eigencats with the physical state, this will give us a 0. So in the sense that these two state in the physicals in physical worlds is orthogonal between each other. So and we want to check that why we want to normalize the physical state. As you can check that we have a version 1.18. recall we have one of the properties of the normalized state, which is the expansion coefficient for the normalized state is with some of the index is equal to 1. And this one is actually given us as the expansion coefficient of a state. Let's say the state can be represented as superposition of the eigenkets. Yeah. So by the properties of normalized state, this one will give us 1. So this one is will ensuring us that will ensure us that the total probability to measure each of these states together be equal to 1. Yeah, this is matched with the probability interpretations also matched with the probability interpretation. Yeah, it's non-negative. Total probability is equal to 1. Probability of AI. Alpha is the physical state. The physical state that can be written as superposition of eigenkets. Okay. The reason one of the reason we want to choose the Hermitian operator to represent our observables, the physical observables, because the eigenvalues of it are always real, and different eigenvalues correspond to the different eigenkets are orthogonal. And previously also postulated that the alpha cat and also C alpha cat, when we multiply the complex number C on cat, it will represent the same physical state. So that's why we want to use the normalized cat to represent our physical state to guarantee that the probability interpretation, or sometimes we call it as a bond statistical interpretation, to be fulfilled. Also, we want when we talking about the probability, because this the physical state, when we measure when we do the measurement on the physical state, this one is not certain already. So it can be, let's say you have some probability to be thrown into the eigenket A1, eigenket A2, A3. So let's say we do the many measurements. We do the many measurements. So we want to see what is the expectation values of observable A. Let's say we want to find the expectation value of measuring observable A in that physical state alpha. So first we define the expectation values of observable A is taking the this expectation value is taking the operator acting on the alpha, and we're taking inner product between these two. Why we want to do this definition? Because if we try to write it down in the in this equation, this will be clear when we seeing this. This will be the probability probability of obtaining A. And this one is a measure values. So let's say this will be the discrete discrete. Yeah, the probability measurement is like when we have a values multiply on the probability of it, and we taking all of it together. This one will give us the expectation value. So by the way, we insert the two identity operator, and as in between the A and alpha bracket. And we let the operator A acting on the cap. So will give us the eigenvalue and also eigencap. And also we notice that these two state, this bracket together is the will give us the autonomality properties, and will give us the Kronecker delta, and it should be put in the front. And we're taking the summation over the index J. So the terms will vanish outside of I equal to J. So the only term that is surviving is the I term. So this one AJ will become AI, and this one will become AJ become AI. And these two can be multiplied together. When we interchange it as become, this will be the conjugate of the first one. The second part, this is actually the second part. I want to talk about this, because it will be a jump on the this one will be the first part I want to present. Yeah, the second part, shall I proceed to the second part? Quite next thing. The position and momentum space, like how we interchange, how we represent it in position space, and how we interchange this physical set into the momentum space. Yeah. Two more weeks. Which contains it. If follow from the previous content, I want to stop at angular momentum part. No, the scattering part. Yeah, it's more to gauge. I wish before I go, I wish to cover until dynamics, which is the scoring equation, how we can see it, when we how we can use the kind of a generator to generate the scoring equation. Yeah. And the second part, before we get into the second part, the idea of the jumping I want to present is, first is a big jump from other mechanism. I mean, this, because I want to present about Pythagorean equation, Dirac equations, in the sense that including the probability density and probability current density. So first, I want to give first the intuition about the Schrodinger equation. So yeah, I will present the probability density and probability current density of the Schrodinger equation, and we move to a Klein-Bode equation, how to derive it, and how to get the derivation of the equation for the second part of today. Yeah. Should I? So okay. Yeah, we start with a we start with a Schrodinger equation, high dependent Schrodinger equation, although we haven't defined it. We haven't get chance to look into it before. So the Schrodinger equation have a form, the partial differential equation. Partial differential equation. This one is the wave function. Wave function in the sense that a physical state is representing in the position position space. So the position space, you can think of like, let's say we have a physical state of alpha, the arbitrary state. The wave function when you're taking the inner product between the position eigen, inner product between the position eigencase with the physical state. This is x. This will be our wave function. And h is our Hamiltonian operator. The Hamiltonian operator is expressing it as the kinetic energy plus with the potential energy. And here Hamiltonian operator, although it's representing the total energy, it is in the non-relativistic version, in the sense that when we cutting out the Hamiltonian operator, sometimes we are using the head, it's not using here. So it's equal to T plus U, where the kinetic energy part as can be expressed as the momentum operator P square over 2M plus with this should be. So as we see here, this one is the non-relativistic approximation. So can say that a Schrodinger equation is not, it only works for non-relativistic particles. So let's say we have a normalized wave function at some time. We prepare a state. The wave function is normalized already. So we want to ask if this wave function that's encoding the information about the particles will be continuous, normalized at later time. So when we're talking about the wave function is normalized already, in the sense that when we're taking the integral between the complex conjugate of a wave function and the wave function over the whole space is equal to 1. So in the sense that when the total probability of that over all space is equal to 1. So we have a question: is this still holds for later t? And we recall back the interpretation of wave function. Just now we have two physical state. Sorry, one physical state. When taking the inner product of itself is the probability density. So it's so we define one of the we define integral of the probability density throughout the space as the nt here. So as the so we want to show that the probability is conserved, is sufficient for us to demonstrate that for later t, the rate of change of this integral will be equal to 0. Means that this the probability density is constant with respect to t. It's not changing. So in a sense that the rate of change of n with respect to t by nt. The whole part equal to 0. The whole part dn over dt equal to 0. It's not necessarily to be true. Probability density conserved means that this whole space have total probability of 1, let's say, and after some time, it's still equal to 1. So it's not changing over the time. So constant and so constant. So that's why we taking the rate of change of this integral is equal to 0. So it's not changing with respect to time. So we substitute the equation 2.5 equal to into the 2.6. And recall back the rho here is defined as the phi star phi. So we are taking the chain rule, taking the derivative of respect to this. So this will give us a product rule of and give us the equation of this. Again, we will use the Schrodinger equation. The Schrodinger equation gives us 2 points. So we are using equation 2.4 with the probability density with rho equal to this one, and also the Schrodinger equation from 2.1. The Schrodinger equation is IH bar over T psi and Hamiltonian acting on side. And we're taking the this one, we rearrange the equation will give us the first part, and for the second part, we taking the conjugate, complex conjugate on both sides, complex conjugate on both sides. So will give us this second part, and we substitute back into the equation, the second line, which will give us a third line of the equation. And we want to recall back for the Hermitian operator in the wave function. The Hermitian operator, it satisfies as it satisfies this integral as if we writing it as in the Dirac notation. This one is actually is so yeah. This one actually the Hermitian operator satisfy this equation, and if we putting back into the equation 2.7, we actually that this 2.7 will be vanished. So dn over dt here is equal to 0, and we hence we say that the Schrodinger equation will do the part on if we prepare a system is have a normalized probability. I mean the physical system is normalized already. At the later time, the Schrodinger equation will do the part, will keep it normalized all the way after the t capacity. Yeah. So this is about the probability density and probability color density of Schrodinger equation. That Schrodinger equation is the probability density of a Schrodinger equation is conserved. And if we further exploring the equation 2.7 here, let's be writing down the full form of the Hamiltonian operator. The Hamiltonian operator, when we express this as the kinetic energy part and also the potential energy part, the kinetic energy part will give us the p squared over 2m, and p is the momentum operator, and m is the mass of it. So plus v. When you're writing down this, substitute this Hamiltonian operator into the equation here. And again, the p, I didn't include it, but the p is momentum operator is bar h over I of Laplace. Maybe this one I wish to cover this for next week. For the momentum operator, how we can get it from get the momentum operator is this. This one actually is in the momentum in the position space. So yeah, the V depends on the potential, external potential. In the front box. So the p squared over 2m together with terms of 2m and p squared in the sense that we adding 2 times on it. So this will give us the negative bar h squared over 2m. This will be nabla dot nabla, so it's square. So when we insert these two equations into, when insert this into the equation, the second line, and we rearrange a bit. So in the sense that the third and the fourth one, we cancel out it. This one I do some physical solution inside is talking about why the operator, potential operator V can be cancelled out because it's assumed to be real. And if the potential is complex, you'll see later this one is the probability here will not, sorry, the probability density here will not conserve. So this, the last two term is cancelled out. And we use the properties of a dot product to arrive at last line. Yeah, when we dot it, it's why we want to express in this form. So actually, if we this is requiring some part of the part about electromagnetism. We define the probability current density. Probability current in the sense that is the sense of the electromagnetism current. So this we define this one when we insert this term inside of it because it's just a number. So we define this together as the probability current density. And if we writing the J into inside in the equation and we put the terms into left hand side, you'll find that this is actually giving us the continuity equation. What we call it as the continuity equation, we can see in the next part. But I want to mention that the conservation of the quantum mechanical probability. Sorry, this equation also known as the conservation of the quantum mechanical probabilities, or also the continuity equation. Similarly, if we recall back on the electromagnetism, this one is actually as the charge density, and this one is the current density in the EM. So probability, yeah, current density. Then written in the wave function is in the, you mean in the form of wave function that is describing the physical state.
A similar form. So J is just some current density.
Current density, yeah. Function, yeah.
In all that current density, right? Can you express it?
For all current density, expressed in this form. Quite get it.
Like a measurement, right? Every time. Anyway.
If yeah,
So you get a function.
the wave function will satisfy this equation.
The wave function. Measurement.
Current and
For the function that number. So it can that function is a wave function. For every current density, find a wave function.
every current density. You mean the probability current density or
That is electromagnetic.
yeah. I'm not sure this get your question correctly applied. In electromagnetism, this is tell us about the continuity equation. In the sense that this is one of the Maxwell equation. Can be derived, yeah. One of the Maxwell equation. For Maxwell equation. Electromagnetism formula is actually this formula. I think so. I mean, in that context, there's no wave function. No, no wave function. No wave function. Yeah. So my question is, get one time. Okay. No. Why not? Why not? We kind of analog to the electromagnetism. So analogy of electromagnetism is when let's say we have consider a closed volume. When in the electromagnetism, the charge flowing out is equivalent to the current is going out in the electromagnetism. So the charge is the charge density of that closed volume will be changing. In the sense of in that analogy, we define the probability current. Let's say if the probability current, kind of the current is flowing out of the closed volume, the probability density or the charge analog to the charge density will be changing. I think cannot express. Because the one is talking about wave function, one is talking about Jian part. In the electron can be expressed in, it's expressed in wave function. Oh, okay. I think this part is about the quantum electron dynamics, when we try to use the wave function to describe the electron, and hence on for the current. In that sense, probably can express it in this, in the form of QED. So this one I don't know. Continue. Yeah, this is like why do I want to bring out this analogy? Because if you thinking of the probability density, the probability current as the EM charge and also the current, and if you're writing the continuity equation, the equation 2.1 in the form of integral over the closed volume, and we're using the divergence theorem. As you can see that this is expressing the flux, the current flux that is leaving out the surface. As you can see, when this is, because it's equal to negative of the flux. So in the sense that when the flux is leaving out, and this one, the left part, which is changing over time, and we can say that the probability density is will be changing. Yeah, this is why we call as the continuity equation, and the continuity equation is important for, if I'm not mistaken, is important for the Noether theorem, and Noether theorem that about we have a charge and we have a current, and this continuity equation will, if it satisfies this continuity equation, the terms will be constant. The terms, let's say this one is the for the probability density. So if let's say we can find another terms that is satisfying this equation, this will measure, will tell us that quantity is, the kind of quantity is constant. In general sense, if we, that quantity when we can be expressed in the equation 2.1. Rho probability and all the good. Rho here is this one. So the n and rho is taking the over the rho. Because of the okay.
So this both side is zero. Why you put zero minus zero? Both side is zero. Because you argue that the del rho del p is zero, right? Left hand side is also del rho over del. So why you put zero?
Zero minus zero.
No. So let's write both of zero. Right? So this whole thing is equal to,
Yeah, equal to 0.
okay. And then why you do the other thing? 2.12, right, you just 0 plus 0 equals 0. Separately, they are 0 already.
Because hash here we express as the kinetic part
Doesn't matter.
of potential.
Doesn't matter. No matter how you express your hash, first row, the two thing is 0. See what I'm saying?
Yeah, this two is 0.
Left is 0, right is 0.
Okay.
So what's the point of putting 0 from 0?
In 0 plus 0.
No. So I don't care about I only care about the
Oh.
first line. First line already now is 0. So the left and right are both 0. So why you write 0 from 0? Why you put two zeros together? I mean the
J is not necessarily to be 0
A is not necessarily to be 0.
because we express the full terms of hash.
But once you put del on J, right, you get 0.
So
Put del on J, delta on J is the first line, right? Delta on J is the first line.
J, this one is J.
This one is delta J.
This one and this
Delta
one.
J.
Uh-huh.
Delta J equals the first line.
This one.
Yeah. So delta J equals the first line.
No. Because we cancel the term of potential part. So actually this is Laplacian.
Yeah, I mean, this is equal, right? So you should be able to go up, go down, right? Equal.
Yeah.
So sure lah. I mean delta J plus the 0 lah. What's wrong with that? Equal meaning I can go up, go down.
Mhm.
So extra lah, never mind lah. I mean, if you want to add any B, then, but the point is this delta J is 0. You can see from the equation.
Okay. Yeah.
Right or not?
Ah.
You agree? You're right. So then what's the point? Like you put something, yes. The thing, okay, when we write 2.12, right? 2.12. When we write that plus that equal 0, meaning there's a non-trivial cancellation there. These two add together, only then they are 0. But just now we already calculated both of them. So what's the point of like them together? They are both 0. The right delta rho over delta T is 0. Delta J also 0. You understand what I'm saying?
Maybe you want to put the analog to EM here to.
Doesn't make sense. Cannot. Something wrong here. Something is wrong here. Doesn't make sense. We cannot simply do stuff on. Even if we say that we can something in somewhere else, you cannot like how to say modify your result. Your result is just delta rho and the delta. Check that first, maybe that or this is what you get. You cannot simply modify your result.
It means that is
Something is wrong here. Something is wrong here. Yeah, otherwise it doesn't make sense. Right, 0 plus 0. It makes sense if you write del rho over del P 0 or del nebula J is 0. We won't put whenever we write 2.12, right? mean that even if both of them are non-zero, their emission.
Oh. What do you think about?
I think maybe you need something. Something in your. I think 2.12 maybe is correct, but whatever you say previous. Want to look at it, but
Let's say we can, I'm not sure, if let's say we can, let's say we derive in these terms, this equality, and we pull up another part about this term is equal to 0, and we deduce that this one by equal to 0.
do two things. This one is not there. That's what it means. A equal to B equal to 0. A equal to you want to deduce A minus B. One way to show is A equals, but I don't think this is what you want. That's more type no zero. That one is more useful. It already both of them is
We move to high order equation. High order equation, the scoring equation that we see about previous part is the non-relativistic framework. As we can see, the Hamiltonian operator is very express the Hamiltonian operator, which is a total energy of a system. Is the kinetic energy part is equal to P square over 2m plus V. So P square over 2m here is obviously non-relativistic framework. If in the relativistic framework, it should be like E, the total energy square in Einstein reaction is equal to mc square plus pc square. So the total energy equal to the these two terms. This is in the relativistic framework. So and this make the Schrodinger equation Lorentz non-invariant, and for it to be whole, for the equation to be whole in the relativistic framework, it must be Lorentz invariant. So as we can see, the first when writing down the Schrodinger equation, the hash here is p square over 2m, so over 2m. This is square plus v. Okay. So we see the derivative of respect to time and derivative with respect to the space is different order, and we say this is non-Lorentz invariant. So and hence unable to describe the relativistic phenomenon such as mass energy conversion of the different multi-particles system. And for now onwards, we will use the natural units and Einstein summation convention later. And one of the approach to correct, unless said otherwise. Okay, but the Schrodinger equation is actually quite works very well for non-relativistic particles such as electrons, protons, etc. But for the relativistic particles such as the photon, the light, which is moving in the speed of light, yeah, it's failed to use a Schrodinger equation to express. To correct it, the Klein-Gordon, one of the approaches, Klein-Gordon equation, it start by writing down the Einstein and energy momentum relationship. Where here also we assume the C is equal to 1, and we promote the energy operator into the we promote the energy terms here, the square here into the operator, and when we acting on the wave function that is describing the single particle system. And also we have the operator, energy operator as promote the energy to the operator as operator, momentum as the operator. Usually it's a I bar hash blah, so hash bar is equal to 1 here. And if we arrange the equation, it will give us a Klein-Gordon equations in this form. And we can see the order of derivative for spatial and also time is in the same order. Both are second order. So in the sense that now the equation is Lorentz invariance. The part that I highlighted yellow, I'm not sure why this is like, for example, this one manifestly Lorentz invariant force, but why this one is manifestly highlighted in yellow color? I don't know. Yeah, it defines the square here is this one. And maybe I should write it down. This is the this one is contravariant for derivative, and this one is covariant for derivative. Yeah, so it's one Lorentz invariant form, and the Klein-Gordon equation has a prime wave solution in the sense that I think we can use the force to solve partial differential equation, which means that is the equation is in the form of like multiple of each other. So, and we can check this one. This solution is indeed substitute back into when we substitute back into the equation 2.18, the Klein-Gordon equation, it satisfies the equation square psi equal to p squared psi plus m squared psi, which we assume in the front part here. Yeah. Yeah, I try it. Yeah. I don't know why he put this one as the Lawrence invariant form.
Why when you write it,
Yeah.
then you need to know the Lawrence like
Lawrence action and
that. So you need
Lawrence
not the
action.
Lawrence. So it's invariant after. So if you write it in this form, I thought you understand. You keep saying Lawrence.
This page is
So this part already got Lawrence.
I think
If you know about what you're talking about here, you should know what you're talking. What's happening? Same thing.
the order is
So if you don't understand that family,
yeah this one.
so you need to find out why this is Lawrence, or why Lawrence. This number. So to answer this question, you need to find out what's the Lawrence. I know you understand.
I can't understand, but not sure why this one
So you
is.
understand because they are the same thing as you. So if you know how to check that one is the non-invariant, then you think
Yeah.
same way of checking. So if you don't understand this, maybe you previous one.
I think this one when you apply the Lorentz transformation will give us the same equation.
I guess give you the same
Equation.
operation.
Then okay.
Obviously, it's same equation, but apparently, I think it's LV.
Why this one is
So
consider two friends. One of the friend is having measuring the side. Another friend is measuring the side prime. And these two friends related by the Lorentz transformation. And this friend and solving the quadratic equation have their form. I think because T and the spatial part and also the spatial part and also the spatial part and also the time part will be changed after the Lorentz transformation in the yeah. So I don't understand why this one any
So you
specific.
need to show it's why when their order is true. Order true, not true.
If different order than different equation, different form of equation. For quadratic equation, we want to find the probability density and probability current density of that equation. And again, we follow the same procedure as and finding out the Schrodinger equation. So expressing by multiplying the terms psi star with the equation 2.18 minus with the psi and multiply with the equation 2.18. Compute complex conjugate of it. And we express this form. This is why we can get a third line, because this is the complex conjugate of the first one, the first term. So when when complex function minus subtract with the complex conjugate of that function, we'll get the full imaginary part of the complex value function. Imaginary part and multiply by 2i. And same goes for the right hand side. And third line. So again, here we wish to again here when we express it in this form, actually we can arrive at the continuity equation. Continuity equation in the sense that this guarantee that the probability of the time quantum equation is conserved because it satisfies the continuity equation. And here we want to because we wish that probability density is in real, and here we can see that if we see that these terms here, this is this one, 2. We multiply with I here in the row and also J to make sure that the row and J is real. The next one, if we are putting the probability current in the four vector form. Four vector form in the sense that the first term is a row and also the another three terms is a vector J. And this one is just a shorthand notation, but it's expressed as the A. Sometimes it's 1/2, but sometimes if you are writing the continuity equation just now, the del rho del t plus with J here, the sense that J is you can write it as the spot. And if first we have the solution, when we have a solution of the quantum quantum equation, we try to substitute into the row here the probability density of the quantum quantum equation, and we arrive at 2 AE, and same goes for probability current density. If we aware that the E here, E squared, starting the E squared plus equal to P squared plus M squared, and the energy can be positive or negative. In the sense that when the energy is negative, sometimes we discard the energy. In classical mechanics, we discard the negative energy solution because it's not matched with our equation, because most of the time the particles in positive energy. But in this way, in quantum equation, actually if we not discarding the negative energy solution in the probability, we are not discarding the negative energy, and we substitute it on the probability density here, you will find that the probability density is negative. So this the quantum equation have some problem on explaining the figure state, because the result is that the negative energy solution have the negative energy negative probability density. Have a physical negative probability density. So this is the first approach to modify the Schrodinger equation to into the relativistic version. The attempts is failed because of the unphysical negative probability density, and the second attempt to modify it is by Dirac equation. The Dirac equation is starting from looking at wave function that why is it failed? Because the probability density here is have a negative part. Or classical mechanics, but then if we are not discarding the negative energy solution, the probability density will be negative. Yeah. Why not discarding? What make in general? Maybe in the classical sense, measuring the energy is positive form. So automatically in our intuition will discard the negative energy part. But then for the particles, the wave function, also the quantum mechanics, we're not discarding it because like the quantum mechanics is not matching our intuition in classical mechanics already. So probably there is some negative energy solution. That's why I want to include. Uh, because probability density is negative. Because probability density usually we are measuring a probability, positive probability. The negative probability kind of not match our intuition.
So the problem is
Yeah. And there's another problem also, but I'm not including it. It's about violation of the speed of light. But I'm not sure how to describe that. Maybe I will include in the notes. But then the idea is that the change of in short term is a violation of speed of light. And Dirac equation is the second attempt to finding the relativistic version of quantum mechanics. So it starts by assuming the first order terms both space and time derivative. In the sense that this one is del over del t here, and p here when we writing out the operator form is the nabla here. So the first order in both space and time derivative. And in the sense that when taking the perfect, in the sense that we taking the square, it will give us the Einstein relation of momentum and energy. It's a perfect square. So, but then the alpha and beta, we yet to know what is the alpha and beta. And And the front part here, because it's a Hamiltonian, and sometimes they're calling it as a Dirac Hamiltonian. If you're writing down a form of equation 2.27, and this is the this P can be expressed as PS, PS, PY, and PJ. In the operator is negative I del over del X for X component, Y and Z for Y and Z component. So the dot product alpha and P together as the
P has the existing thing. No, we don't know what. Have it.
math.
Yeah.
Okay. Energy. Energy. Energy operator is fixed. Is here. Get down.
The alpha and beta.
We're squaring the both side of the equation together and arranging the terms, and we want it to be reduced to the form of Klein-Gordon equations. So by comparing the both equation, the Klein-Gordon equation, and also this full form of the Dirac equation, we will get the, like for example, this AXY alpha XY alpha Z square there is equal to here must be equal to 1. And these terms, 3 terms, and also this one need to satisfy this anti-commutation relation. Where we define anti-commutation relation, for example, for A and B is equal to AB plus BA. So the alpha and beta need to satisfy these 3 equations. And we arguing that alpha and beta, perhaps it can be the numbers. But then if we taking the j equal to 1, k equal to 2 into the equation 2.34, it will give us the ax. This one is correspond to x. One is correspond to y. So x alpha x y equal to negative alpha y x, which implies that we factor out together. Right. Alpha, which implies that this alpha x equal to 0 or alpha y equal to 0. And also, but then from the equation 2.32, the alpha x squared equal to alpha y squared equal to 1. So it cannot be just a number based on these 2 equations. So the another object that we want to consider in the B is a matrix. Alpha and beta is a matrix. And recalling back the some of the properties of trace of matrix ABC is equal to trace of BCA, matrix BCA. By writing down, we change the ABC to BCA here. Okay. ABC. yeah, ABC, we arrange 2 times A, B. And using the properties of beta alpha I beta equal to negative beta alpha I, we arrive at the
I
angle.
don't think you want to use ABC. AB,
Oh,
confusing. You are treating BC as one.
oh,
So you take AB. Then you copy.
we substitute this into the equations, the trace of it, so it's negative of the trace, and the beta square is equal to 1. So we found that the trace of the alpha I is equal to 0. So it's a traceless matrix. And moreover, if we apply the alpha I on the eigenvector to give us the eigenvalue of alpha I, and because alpha I is equal to 1, when apply the 2 times, so because lambda is just a number, eigenvalue is just a number, and you give us the lambda eigenvalues equal to positive negative 1. And same goes for beta. So far we have the alpha beta is traceless matrices with eigenvalue of plus or minus. So using the fact that the sum of the eigenvalues of a matrix is equal to its trace. So the only way the trace can be 0, traceless, is when the alpha I beta matrices are even dimension. Because even dimension, positive, negative, and trace together is equal to 0 when we use the eigenvector as basis. Diagonalize the we get, yeah.
So you get eigenvalue of eigenvalue can be.
Hmm. And because you are Hamiltonian, the Hamiltonian operator, it must be represent the energy observable, so it must be a Hermitian operator. The alpha, hence the alpha and beta must be Hermitian. I think it's alpha. Maybe we stop at the next slide. Okay, so finally we arrive at the end of alpha and beta form mutually anti-commutating Hermitian matrices with an even dimension and trace 0. I think this one is no, sorry. When if we consider first even dimension is 2-dimension, the intuitively the matrices that we want to find, maybe just a polyspin matrices. It can be different representation. This is one of the representation as polyspin matrices. So we are considering maybe this is the lowest dimension. Maybe the dimension of the alpha and beta is 2-dimension. But then at the end, if you want to satisfy the 3 equation before, two anti-commutating equations and also the R square blah 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 equal to 1. And if you want to satisfy these three, but at the it turns out that the two dimension we cannot do this. We cannot find this four of the anti-commutating matrices. So we move to the next one, which is 4 times 4 dimensions. And we actually can find in 4 dimension, 4 times 4 matrices, which actually can find the five mutually commutating 4 times 4 traceless matrices. And I think this one is related to Clifford algebra. I'm not sure how is it. I just having this so I include. And so we conclude that this one, the matrices alpha beta is 4 times 4 matrices. And when acting on the sign, we force the sign, the wave function become the 4 components wave function. Yeah. Now, do you understand?